So today we'll go over hemoglobin and myoglobin. I understand that it's confused quite a few people, so hopefully I can clear things up a little bit. But it is quite a complex topic, so it's okay if you're a little bit confused. So first of all, we'll have a look at the globin protein. Okay, so globin protein, it's made up of 8 alpha helices, and each alpha helice is named or labeled A to H. Okay, so A, B, C, D, E, F, G, H, and each globin protein is about 150 amino acids long. In the case of myoglobin, it's about 152 amino acids. For the alpha subunit of hemoglobin, it's about 142, and then the beta subunit is about 146. You don't have to remember those numbers, but just keeping in mind that the globin protein is very similar for both myoglobin and hemoglobin. They just have very slight differences in both their length and the sequence of amino acids. So their primary structure, remember I said yesterday that the sequence of amino acids is the primary structure. Okay. And it has the globin protein has a hydrophobic pocket where the non-polar heme molecule can bind. Okay. And then the histidine F8 on the globin, so that's the 8th residue. Excuse me guys. Can you guys just keep it down, please? Can you guys just keep it down, please? Yeah, cool. So the 8th residue on the F helix, that's histidine F8, and that binds by coordinate linkage. So a coordinate bond is where both of the electrons in the covalent bond is donated by one atom, whereas a normal covalent bond you normally have one electron donated by each atom. Okay, that's not too much of a biggie, but that's what's happening there. So it's coordinate linkage, which is a covalent bond to the Fe2+, so the iron atom of the heme group, and then the histidine E7, which is on the other side of the heme group, does not bind to the heme, but causes oxygen to bind at an angle due to steric hindrance. Okay. And that the angled binding, that prevents the oxygen from binding too tightly, and so it allows the oxygen to be released in the tissues where it's needed. Okay, so you can imagine that hemoglobin is a bus, and then in the lungs the oxygen can get on the bus, and then at the tissues they need to get off the bus. But if hemoglobin is holding on to the oxygen too tight, then that's not going to allow the oxygen to get off at the tissues, right? So it needs to be secure enough to hold on to it, but also not hold on too tightly, and that's what that histidine E7 is there for. Okay, to provide steric hindrance to prevent the oxygen from binding too tightly. And then the iron, it has to be in the ferrous 2+ oxidation state, because if it's in the ferric state or the Fe3+ state, it's not going to be able to bind oxygen at all. Okay. So I'll just quickly draw that heme group. Okay, so in the middle of the heme group, you've got the Fe2+ ion, right? And it's bonded to the heme group. Okay, so you've got the Fe2+ in the middle of the heme group. Okay, and then so below you're going to have this cylinder is representing helix F. Okay, so remember that in protein structure shorthand, cylinders represent alpha helices. Okay, so this is an alpha helix, and in particular this is helix F. Okay, and on helix F there's a residue. So this one here, this one is histidine F8, okay, and that forms a covalent bond, a coordinate linkage with Fe2+, and so that also holds, this also holds the heme group in place and prevents it from floating away. Okay, and so on the top you're going to have another alpha helix, and this one is helix E. Okay, and so there's going to be this one is histidine E7, okay, and that's just going to prevent oxygen. So if histidine E7 wasn't there, oxygen would bind like that, but that's going to be too close to the histidine E7. So in the presence of the histidine E7, oxygen is going to bind at an angle like this, and that's going to be a weaker bond. Okay, and that's going to allow release of the oxygen at the tissues. And so remember that this heme group, the heme group is non-polar, right? So if the heme group is non-polar, you're going to want to create a hydrophobic pocket for this heme group to sit in. So all of these, all of the side chains in this alpha helix that are pointing this way, they're going to be non-polar side chains, right? So these are all non-polar. So that creates a hydrophobic environment for the heme group, the non-polar heme group to sit in. So this is a non-polar side chain, okay? All right. Cool. And so turning over the page, we've got the heme group. So the heme group is a non-polar molecule, and so the heme group is not a protein. It fits into the hydrophobic pocket of globin. And the heme contains a Fe2+ ion, so it can form 6 coordinate bonds. So 4 of these are to the heme group, which I just showed. And then the 5th one is to the histidine F8. And then the last one is available for oxygen to bind. Okay. So normally the heme is a dish shape, so it's domed, right? But then when the oxygen binds, it's going to pull down on the oxygen, and so I should say the binding of oxygen pulls down on the Fe2+ ion, and that flattens out the heme group, which in turn pulls on the histidine F8 residue. And remember, the histidine F8 residue is connected to the rest of the helix, and so that's going to pull on the whole protein, and that's going to cause a conformational change or shape change in the whole protein, and that's going to promote the R state. Okay, so oxygen binding itself promotes the R state due to the conformational changes that occur. Okay. And then, so we'll talk specifically about myoglobin. So myoglobin is found in muscles. So the word myo means muscle, and it's not normally found in blood. Okay. If you found it in blood, that means your muscles are all breaking down. So that's not a good thing. It acts as a storage molecule for oxygen, and it has high affinity for oxygen. So it will only release oxygen when the partial pressure of oxygen inside that muscle cell or the myocyte is very low, so below 10 millimeters of mercury, like when you're exercising. Okay, and just a note there that 1 torr is equal to 1 millimeter of mercury. There's a very slight difference, but it's insignificant as far as we're concerned. And it is a monomer, okay? So it's made up of 1 subunit. And so the shape of the oxygen dissociation curve is going to be hyperbolic, okay? So hyperbolic means that there's, since there's no cooperativity, okay? And each myoglobin molecule has 1 heme group, and so it's going to bind 1 molecule of oxygen. And lactic acid can bind to myoglobin at a site other than where oxygen binds. And so if you have a molecule that's acting, which is regulating the action or changing the action of a protein, but it's not binding at the active site, you call that an allosteric regulator. Okay, so allosteric means somewhere else. Okay, so it's because it's lowering the affinity for oxygen, it's an inhibitor. Okay, so if you were to draw the oxygen dissociation curve for myoglobin on the y-axis, you would have the degree of saturation. Okay, so at the top you'd have 100%, and then at the bottom, so this would be 50%, and then at the bottom you've have 0%, and then on the x-axis you'd have the partial pressure of oxygen. So we just say PO2, that represents the partial pressure of oxygen. Okay, so we'll just say this is 100 millimeters of mercury. Here's 50. Okay, so for myoglobin, it's going to be at, if you have 0 millimeters of mercury, so if there's no oxygen, then what's the saturation of myoglobin going to be at 0 millimeters of mercury? Yeah, 0. Okay, so if there's no oxygen, obviously there's not going to be any oxygen bound. Okay, and then if you increase the oxygen pressure to 1 millimeter of mercury, remember that myoglobin has very high affinity, so it's going to bind nearly all of it that it can. So it's going to go up very quickly. Okay, 2 millimeters of mercury is going to bind all of that right away. 3, 4, 5, and by the time it's about 5 millimeters of mercury, it's going to be 50% saturated. Okay, and then that's just going to keep increasing in a linear fashion until we get to about 90%, and then it's going to flatten out. Okay, so the reason that it flattens out once it gets to this point is that no matter how much binding affinity something has, some of it's always going to be letting some of the oxygen go. Letting go of some of the oxygen. So yeah, that's why it's very hard to get it to 100% saturation. All right, that's just due to like the kinetic energy. Yeah, so this curve here is hyperbolic. Okay, and that's very important to remember, the shape of your curve. And you always get a hyperbolic curve if there's no cooperativity. So then we'll move on to hemoglobin. So hemoglobin, it functions as an oxygen transport and delivery molecule in the blood. So this means that it has to bind oxygen, but also let it go. And each hemoglobin molecule can bind 4 oxygen molecules, 1 for each heme ion. So it's a tetramer, which means that it's made up of 4 globin polypeptide chains. If you want to be specific, it's a heterotetramer because it's made up of 2 different subunits. So there's 2 alpha subunits and 2 beta subunits. But they didn't put that in the lecture slide, so I wouldn't worry too much about it. And then the quaternary structure is stabilized by non-covalent interactions. So remember that if you have more than 1 subunit, if you have 2 or more subunits, you're going to have a quaternary structure. So the quaternary structure is the shape of the molecule made up of all the different subunits, okay? And if you have a change in the tertiary structure of 1 polypeptide chain or 1 subunit, that's going to influence the shape of the neighboring subunits as well, okay? So it has lower oxygen affinity compared to myoglobin, and it shows positive cooperativity. So it's important to say it has positive cooperativity because there's also something called negative cooperativity. So just make sure that you say that when you talk about it, because they like to ask about it in the final exam, about hemoglobin. They might make you write like a whole page on it. And so this means that the binding of oxygen to 1 subunit makes it easier for the next subunit to bind. And so then the shape of the oxygen dissociation curve is going to be sigmoidal. Okay, so let's draw the oxygen dissociation curve here for hemoglobin. Okay, so at 0 millimeters of mercury, again, you're not going to have any, I'll do it in green, so green for hemoglobin. So at 0 millimeters of mercury, you're not going to have any hemoglobin bound to oxygen, okay? But when you introduce some oxygen, so let's say now it's 1 millimeter of mercury of oxygen, it doesn't really increase that much. So even if you get to about 10 millimeters of mercury, it doesn't really change that much. So even when you get to 10 millimeters of mercury, not a lot of hemoglobin actually binds to oxygen because it's got low oxygen affinity. Okay, but then eventually, if you increase the oxygen concentration enough, then at some point the first oxygen is going to bind to the first subunit of hemoglobin, okay? And once that happens, the next subunit is going to bind the second oxygen easier, right? Because then, so then you only have to increase the partial pressure a little bit for your saturation to increase very rapidly, okay? So from this point, for every little increase in the partial pressure of oxygen, you get a big increase in the saturation of hemoglobin, okay? And then once the second oxygen binds, it makes it even easier for the third oxygen to bind, and then that makes it easier for the fourth oxygen to bind, okay? So we're going to have a very steep very steep gradient at this point in the middle, and then eventually that's going to flatten out again, just like, okay, so you get this S-shaped curve, and that's a sigmoidal shape, okay, and that's due to the positive cooperativity, due to that multiple subunit. Okay. Okay. So then, hemoglobin can be in two states. It can be in the R state, which is relaxed. Okay. So if it's in the relaxed state, right. We can just look at that diagram. So the diagram on the picture on the left, in the R state, you can see in the middle, there's a very small gap, whereas on the right, for deoxyhemoglobin, which is in the T state, or the taut state, it's got a big gap in the middle, okay? So that allows for the binding of something called BPG, okay? So BPG is produced during glycolysis. So when tissues are active, they're going to produce BPG, and that's going to bind to the middle of the T state and stabilize that T state. And yeah, so active tissues produce BPG, H+, and CO2, which can all bind to hemoglobin and stabilize the T state of hemoglobin, thus increasing the release of oxygen. And BPG, yeah, so I said that. And then the concerted and sequential models, I know that it's very confusing, but I wouldn't really worry too much about that one. Just know that hemoglobin kind of can be explained by both models. Okay. So on the next page, we want to talk about, we want to draw in the factors that cause a left shift and a right shift in the oxygen dissociation curve of hemoglobin. Okay, so we've got our, I'm just going to rub out the curve for myoglobin. So we've got the curve for hemoglobin here. And so we can have a left shift, which is where the whole curve is moved to the left, like this. Or we could have a right shift, which is where the whole curve is shifted to the right. Okay, so first of all, we'll talk about the left shift. Okay, so the left shift has higher oxygen affinity. Okay, so that's going to be caused by decreased levels of BPG will cause it to have a left shift, and also decreased levels of carbon dioxide will cause a left shift, and an increase in the pH. So if you have an increase in pH, that means you've got a lower concentration of protons. Okay. And then a right shift means you have a lower oxygen affinity, and that's going to be caused by the opposite. Okay, so you're going to have increased levels of BPG, increased levels of CO2, and lower levels, a lower pH, which means that it's more acidic. Okay. So I want you to remember these conditions here, which the factors that are going into the left shift and the right shift, okay? So now we're going to draw a little diagram. Okay, so I'm going to draw a heart. Okay, so here's our heart, and then we have our lungs. Okay, and so blood goes from your heart, it gets pumped through the lungs, so it gets oxygenated. Okay, so it's going from the you have deoxygenated blood coming out of the heart, and then it's going to pick up oxygen from the lungs. Okay, so in the lungs, what do you want to do? You want to pick up oxygen, right? Okay, so what's the conditions in the lungs? In the lungs, the partial pressure of oxygen is high, so it's about 100 millimeters of mercury. Okay, and then the levels of BPG in the lungs are going to be low, and you're breathing off CO2, so carbon dioxide is going to be very low in the lungs, and there's no active muscles producing lactic acid or protons, so the pH is going to be relatively high. Okay, so all of this is going to promotes the R state, which causes a left shift. Okay, so, and the left shift means that we're going to pick up more oxygen. Okay, so then once the oxygenated blood comes in, it's then going to go out towards the body, right? Okay. Okay. So we have our this is our active muscle here. Okay. So if the muscle is working hard, the partial pressure of oxygen inside the muscle cell can be as low as 2 millimeters of mercury. Okay, and it's going to be producing a lot of BPG. Okay, so you'll have lots and lots of BPG in that muscle cell, and you're going to have lots of carbon dioxide inside the muscle cell, and you'll also have a lot of lactic acid being produced, which means that it's going to have a low pH. Okay, so it's going to be quite acidic. And remember that inside the muscle cell, you've got myoglobin, okay? So if the partial pressure of oxygen drops below 5 millimeters of mercury, myoglobin is going to be supplying oxygen, okay, to that muscle cell. But there's not a lot there, so that's not going to last very long. So it needs to pick up oxygen from the blood, okay? And so this is the capillary, okay? The capillary that's supplying the skeletal muscle, okay? So the partial pressure of the venous blood is about 40 millimeters of mercury, okay? So have you guys gone over this in hubs yet? Yeah, so the venous partial pressure of oxygen in blood is 40 millimeters of mercury, and you're going to have higher BPG, higher CO2, and lower pH, okay? So this all means that here, this promotes the T state, which causes right shift, okay? And if you have a right shift, that means you have lower oxygen affinity, and that means you can release more oxygen where we need the oxygen here, okay? So all of your oxygen is going to go into the blood, and the CO2, the carbon dioxide, will also be picked up by the blood. And so also hemoglobin can also carry carbon dioxide. So carbon dioxide can bond. If you have, this is the N terminus of your hemoglobin molecule, so your globin protein, the N terminus, you're going to have an H. So normally you'd have you'd have 3 H's, 3 hydrogens bound to the N terminus, right? But if there's a lot of carbon dioxide, it can bind to the N terminus of the globin protein. And so hemoglobin can not only carry oxygen, but it can also carry carbon dioxide away from the skeletal muscle, okay? So that's quite useful, isn't it? Okay. I think that's it. And then, so then we'll talk about so we'll quickly talk about fetal hemoglobin. They used to have 3 lectures on hemoglobin and myoglobin, but I don't think they're really going to examine fetal hemoglobin this year. That's what I was told, but I think as long as you know that hemoglobin in the fetus has a higher oxygen affinity than adult hemoglobin, which is known as HbA, okay, for adult hemoglobin. So that's necessary for the oxygen to get across the placenta from the maternal blood to the fetus, okay? And so at high altitude, you're going to have one of the first physiological adaptations that occur is going to be an increased production of that BPG, okay? So if you have more BPG, will it cause a left shift or a right shift? So if you have more BPG, yeah, so there'll be a right shift, okay? So if you have a right shift in your oxygen dissociation curve, you're going to lower the oxygen affinity, which means greater oxygen unloading. So it might be a bit confusing because you might think if there's less oxygen available, why would you want to decrease your oxygen affinity? But it can be explained by looking at your oxygen dissociation curve and where it's actually flat. Okay, so this is your 100%. This is 50%. And then you have 100 millimeters of mercury. You have 50, 25, 75. Okay. So normally at sea level, normally your arterial blood is going to be 100 millimeters of mercury, right? So it's going to be 100% saturated. And then your venous blood is going to be about 40, right? So if you go up, that's going to be about 70%. Okay, so that means that the gap between arterial blood and venous blood is about 30%. Okay, so you've delivered 30% of your oxygen to your tissues. Okay, now if you at high altitude, the partial pressure of oxygen can only get to a maximum of about this much here. So my graph isn't completely accurate, but it only gets to about 60 millimeters of mercury. Okay, so then this here will equate to about, we can only achieve about 90% saturation in the lungs. Okay, and then assuming that your venous partial pressure of oxygen is still 40 millimeters of mercury, then you're only going to get 20% of the oxygen delivered, which means that you're not getting enough oxygen to your tissues. Okay, but if you increase your BPG, then what's going to happen to your oxygen dissociation curve? It's going to shift to the right. So it's now going to be like this. Oops, so it should be more like that. Sorry. So then at the same you've got the same arterial partial pressure of 60 millimeters mercury, but then because of this right shift at 40 millimeters of mercury, you can deliver more oxygen. Okay, so that's going to be a greater, you'll deliver the same 30% as before. Okay, so that's a bit complicated, but don't worry too much about it. Yeah, and then we've got hemoglobin. Okay, so the Fe2 plus ion on one subunit is oxidized to the 3 plus oxidation state, which means it can no longer bind oxygen. And the other 3 subunits get locked into the R state, which hinders oxygen release at the tissues. And so an example of a mutation is methemoglobin Boston. Okay, so that can cause methemoglobinemia. And because they just named it that because it was found in the city Boston first. Okay, so methemoglobin is brown compared to oxyhemoglobin, which is going to be bright red. And deoxyhemoglobin is a darker red. And that's due to the different forms of hemoglobin absorbing different wavelengths of light. So I'm sure you've all seen this if you've gone to the supermarket and you buy red meat. If it's fresh, it's going to be bright red because all of the blood is in the oxyhemoglobin state and it's in the 2+ oxidation state. But if you leave it for a few days in your fridge, it's going to go brown. So as the hemoglobin in that meat reacts with the oxygen in the air, it's getting oxidized into the 3+ state, which is why it's going brown. Okay, so that's an easy way to remember that one. And so this oxidation of iron is happening all the time because we always have a lot of oxygen, and the oxygen is going to oxidize our Fe2+ into Fe3+. So we have to have an enzyme inside our red blood cells that can convert Fe3+ back into Fe2+. Otherwise, we'd have too many red blood cells that couldn't do their job. So this enzyme is called cytochrome B5 reductase. And it uses a coenzyme called NADH, which we'll learn a lot more about later on in the course, okay, when we do metabolism. And then sickle cell anemia, this is a mutation in hemoglobin where a polar amino acid is replaced by a non-polar amino acid. So if you had a polar amino acid, where would you normally find it? On the surface or the core? Yep, so it would normally be on the surface. So this polar amino acid would normally be on the surface, but you've got a non-polar amino acid there instead because there's been a mutation. So that's going to cause a problem. So that causes a hydrophobic pocket to form on the surface of the deoxyhemoglobin. And that hydrophobic pocket allows other hemoglobin molecules to stick onto it, like you can see in the picture below. And that means that long chains of hemoglobin form, and that deforms the red blood cell into the shape of a sickle, which is why it's called sickle cell anemia, and it causes it to get stuck in capillaries. Okay, so if you look at a normal red blood cell, it's nice and circular with a little bit of a dimple in the middle. Okay, so it's a nice donut shape which is flexible, and that allows it to squeeze through the capillaries, because remember your capillaries get very, very small. But if you have sickle cell anemia, it's going to be very flat and stiff, so that's going to get stuck in your capillaries, and if that happens, that's not a good thing. Okay, but it's been evolutionarily favored, because if you're heterozygote for the sickle cell, then you're more resistant to malaria, because the malaria parasite lives in the red blood cells. Okay, so having one of these is sometimes advantageous, which is why it's persisted. Okay. Yeah, so that's it. Thanks. Thank you. I'll stick around for a bit if you have any more questions. Cheers.
So, I really don't understand this graph.